You have learned a lot about dot product and cross product. You have probably solved all the complex problems in vector analysis. Then what is this video all about? Why I'm going to teach you again about dot product and cross product? Well, have you ever thought that what is the real meaning of dot product and cross product? What is the difference between them? Why at all do we need cross product? Life would have been easy without these complexities, right? Then why do we need a cross product? Even if we need, do we really need it in terms of solving real problems in life? How does it affect the real applications? In this video, I'm going to talk about the real difference between dot product and cross product. I'm also going to give you a very deep, intuitive understanding of what is this multiplication of vectors are all about, and most importantly, why do we need cross product? Can we do anything without a cross product? So this is the particular purpose of this video, to give you a deeper understanding of dot and cross, the exact difference between them, what is the practical application that is used in real life, and a clear, comprehensive understanding. My name is Shaunak and you're watching this video on Physics for Students. I welcome you to my channel. Before we start ahead and go with the video, let us quickly have an idea about what the two topics we are covering. In order to go and understand the geometric meaning or the difference, don't you think that we need to understand the basics? What is a dot product? What is the geometric meaning? What are actually the projections of vectors and their algebraic properties? And what are the important properties of dot product? What is cross product, their algebraic properties, their geometric meaning, and what are the important properties of cross product? What are the real life applications at all in dot and cross product? And can we use dot products in general relativity? And what is the difference? There's a very, very interesting question which I'm going to ask you. Probably if you know the answers, you can put it in the comment box. And finally, we will come to the summary part. So this is a good time. Let us start ahead. Okay, so first we will learn in brief that what is actually a dot product. Well, as per the definition, it goes that dot product is a mathematical operation between two vectors that produces a scalar as a result. It is commonly used in physics, but what is the actual meaning of the dot product? So here it is on your screen. It shows that it produces a scalar and it represents how any two vector quantities overlap with each other. And the physical meaning of the dot product is that it represents how much of any vector quantities overlap and how similar two vectors are. Now here is an example. Now, when I say two similar vectors are, then I might say that, okay, this is Mr. X and that is Mr. Y, and these two people are more or less similar to each other in terms of their skin complexion, in terms of their accent, in the terms of what they talk. Now, when we say that these two people are similar to each other, what are we trying to do? We are trying to either compare or find out a property which would help us in further analyzing the characteristics of these two people. So that is an intuition behind the dot product, that it shows out that how two similar vectors are, and it is an algebraic operation that will take two equal length sequence of numbers, and ultimately it will return a single number. So the basic intuition behind the dot product is to get a scalar quantity and to know how the vectors are overlapping and how similar two vectors are, just like how similar two people are in terms of their characteristics. So it is easier for us to first understand a geometric definition. The reason behind it is that if we see the graph and the vectors, then it becomes easy for us to understand rather than directly going into algebraic definitions. So if I take an x and y axis and get a vector something like this u and something like v, and then we get an angle of theta, and then I drop a perpendicular. So you see now what I am doing is that this blue line is something which is along the vector u, and this line is basically denoted as this. So the dot product is a measure of how much vectors are aligned. So if you have two vectors, the u and v, the dot product between these two would give the length of the vector along the vector u. I repeat, is the length of the vector along the vector u, which is also called the projection of u. Now, the reason is that when I'm talking that one vector is along with that another vector, that means I'm trying to say that I am moving along with you. This person is moving along with me. That means there is a person or a character which is something similar to each other. why we are trying to find the similarity. That is basically the kind of I would say a mystery that we are trying to solve. So let us see that we get a vector u and we get a vector v, and we are trying to find out the length of the vector along the vector u. That means something is traveling along that vector. And in mathematical definition, what we do is that we represent this as projection of v along u, and this is actually what we do. So here u and v are vectors, so these represent the magnitude of the vectors, and this is actually the angles between two vectors. So cos theta is something which gives the angle between the vectors. Remember that we are trying to find out something moving along with something, and that is the reason we call dot product measures how similar two vectors are. So I hope till now you have understood the basic motivation behind the dot product is to definitely do calculations for physics and mathematics, but something which gives a similarity, and you will soon see that general theory of relativity actually uses a lot about dot product. Okay, so let me give you an algebraic definition. We start with two spatial dimensions, and suppose we have two vectors, say a1 and a2, and b is equals to b1 and b2. So in the case of a dot product can be defined as this. So what we are doing is this one. We are taking the corresponding components and multiplying them and adding everything together. So the a1 component gets multiplied with the b1 component and the a2 with the b2 and so on. This is a kind of a very simple it is a definition of two spatial dimensions. But in case if you want to carry forward the dot product up to n dimensions, it might happen because we are dealing in physics with higher dimensions. This is how we do. So if we get a vector a1, a2 which spans up to an, and b equals to b1, b2 which spans up to bn, then we get something like this, right? So it says a dot b equals to the sigma of I ranging up to the value of n, and it goes a1, b1, a2, b2, a3, b3, so on, and up till it completes an, bn. So this is the algebraic definition. Try to understand that the basic motivation is again to find the similarity of vectors, that we say that vector of u or v is along with some other vectors. Okay, a quick demonstration, a few of the numerical examples I'm sure is going to help you. So if you're trying to get a dot product of v dot w, where v is 5i plus 2j and w equals to 3i minus 7j, then what we get is that v dot w equals to this formula. We just plug in those values and what we get, v dot w equals to 1, right? On the right hand side you see another a little bit kind of a complex I would say numerical terms where u is given, v is given, and d is given, and we're trying to find 3u dot v plus w. So the first approach that we will take is that we will find 3u, which is 3i plus 3j, and we plug in those values. So we get 3i, this is 3 multiplied by 3, this gives to 9j. Next, what we do is that we try to find out v plus w. So if I'm going a little bit too fast, the reason is that the basic idea of this video is to find out the difference. However, I'm just giving the algebraic definition along with some numerical examples so that it becomes clear. If you want, you can take a pause on the numerical part and take a screenshot and you can understand it better. So v plus w equals to this, and this leads to this, and we find out 3u plus v plus w. So we have found v plus w equals to 9 minus 3j, which is quite simple. Then we go forward with this, and when we calculate 3u plus v plus w, again substituting these values, we get minus 27 and minus 27, which gives us a nice 3u dot v plus w gives us minus 54. So this is just a quick kind of an example which will help you understand that when we are learning dot product, can we use the numbers, plug in, and get a kind of a nice exercise. Okay, where do we stand now? Now we are going to understand a quick intuitive understanding of the geometric meaning. Because as I told, geometric meaning are much easier because it deals with much more of figures rather than numbers. So if I given two vectors a and b, and if theta be the angle between them, then the dot product is given by a dot b equals to ab cos theta. And remember, the dot product encodes information about the angle between two vectors. When I say that it encodes information, that means the angle actually cos theta is very, very important because it will give the information what is between two vectors. Okay. So we can also, write theta in terms of an arc cosine or the cosine of inverse, which gives the value. And we know that cosine achieves its most value when theta equals to 0, that means it's positive. When theta equals to pi, when it is negative. and when theta equals to pi by 2, that is smallest. Okay, so what I'm trying to tell you is that explicitly, if I talk that the cosine achieves this value when the values of theta changes, and explicitly I can tell this, right? Cos theta equals to this, cos pi by 2 equals to 0, and cos 0 equals to 1. Okay, so far so good. But can we plot those values geometrically in order to get the angles? That would be easy for us to understand the geometric intuition, right? So let us see that we can do that. So this is one which has got the opposite directions. This is another which has got a perpendicular one, and this is what which has got the same direction. So when A and B are going exactly opposite direction, the first one which has got a red dot, right? This is where it is going in exactly opposite direction. So the dot product will be as negative as possible. In the other case, when you see the A and B are perpendicular to each other, the dot product will be 0, obviously. And on the far right hand corner, I have plotted something which is going in the same direction. That is, both of them are headed so that you see that things are overlapping with each other. That means the dot product will be as positive as possible. So here comes the first difference, and the first important part is that when the values of theta changes, how the vectors are aligned in opposite, perpendicular, as well as in same direction. Okay, so can we summarize in this way? We can tell that the dot product measures how similar two vectors are or how well they travel together, right? So again, I'm saying that this is extremely useful in practical sense, especially in general relativity. We will see certain quick examples. And when we know that we are traveling together, that means I am traveling with my friend, you are traveling with your mate, right? So if you both are traveling together, that means that there is a kind of a similarity, and this similarity will be in terms of characteristic, right? Just remember that if you're going out for a tour with your friend or your family, then you travel along with your family or your friend. The reason is that there is a common characteristic. It might be that you eat the same food, you watch the same movie, you want the same kind of a color on your hat. So that is why you're traveling along with each other. So parallel is something will be as big as possible, and perpendicular will be the dot product will be 0. So when the dot product will be as big as possible, and if the vectors are perpendicular, that means it will be 0, just I have given. Now also consider the argument above, which I have shown actually boils down to one particular equation. And let us say that the vectors are A and B. Then if two vectors are perpendicular to each other, then the dot product is equal to 0. This is a caveat. This is an extremely important information we need to remember. But if you see in this, I'm not going to explain. This is an inequality which persists between dot product, and it is called a Cauchy-Schwarz inequality. It is a big subject. I'm not dealing with that. You can look into internet or others, and if you want, I can make a video separately on this. And it gives us an alternative way to summarize what we talked about the Cauchy-Schwarz inequality. So till now what we have understood is that dot product gives us a scalar. Dot products measures vectors along with each other. When something is moving along with each other, that means we are trying to find a similarity, and that is why we tell dot products are to find out how similar the vectors are, right? Now dot products also serves as a projection of vectors. Now what do we mean by projection? Let us see. Okay. So as the dot product gives us a way to measure similar how vectors are. The problem with the dot product is that it spits out a number, right? So it returns a scalar. So sometimes in mathematics and physics, we want to measure how well vectors travel together while we want to preserve some information about direction. That means we are trying to find out what is there, but we are trying to preserve the direction. So you can say, in other words, we want a dot product like measurement that returns the same information, which is a vector rather than a scalar. Now, how do we do that? That is the question. How do we do that we find out a vector instead of a scalar? Well, if you're given two vectors, A and B, the quantity A and B, they're traveling with together, then we can reframe our word, and we can say that it is our reference direction, and say that A dot B actually measures how well B travels in the direction of A. So A dot B, here it is, it says that how well B travels in the direction of A. So since we want to preserve the information, we really don't want to lose it, then we can just multiply A dot B by another vector B. Yeah. So we should instead multiply the dot product by another vector A in direction. Why? Because we want to preserve the direction, and this is how exactly it happens, right? So here is the one which I have highlighted. We have just multiplied by a unit vector. So it's quite simple. Now the problem, there's a problem. The problem is that here is that the length of A is going to, it is not going to fix up. It is going to mess up our measurement. So to be safe, we can instead multiply the dot product so that we can preserve the direction. So here it is. Now, we can normalize the coefficient of our vector by dividing one more by the length of A, and this is how it happens. Now, remember that since A is our reference direction, we don't want the length of anything which will, create a problem. It messes up things. So we could normalize the coefficient of our vector by dividing one more length, which is this one. Now this is normalized vector that we call, here it is, normalized version of the dot product. So we give this measurement a new name and we call it the projection of B onto A, and this is written as this, right? So the coefficient of our vector is by dividing one more times by A, so that it is called a normalized vector version. Why we are doing? We want the direction or something which will give a vector, and we want to preserve the direction, right? Okay, so it is called the projection of B onto A. Yeah, represents the component of B in the direction of A, and these are the parts. So this reason is called projection because it has a very nice and geometric expression. I mean to say vectors A and B, proj A, B. This gives a vector that represents the components of B in the direction of A. In other words, if we really smash down B directly on top of A, then what happens is that we get, okay, this is same equation, we smash it down and we get something like this, which gives something like this. Okay, so just to quickly recap, this is the visual demonstration of smashing down and how the projection looks like. So if we smash down A directly on 2 and it gives the component of A in the direction of B, then we get something like this. So what is the utility? Utility is that the projection gives us a way to make orthogonal things, which is not the subject of this video. Just understand that by connecting the endpoints, we get a vector orthogonal to our reference direction. So this is something just I wanted to tell you, that the projection of vectors, why it is important, because we are trying to take the dot product on and we're trying to find out that can we get a scalar, a vector instead that of a scalar. Right. Now the problem is that can we extend it to n dimension? Yes, because we need n dimensions in physics and mathematics, and this is a simple formula, nothing much to say about, which extends the dot product up to n dimensions. Okay. So now we come to the algebraic properties of dot product. So we are dealing with dot product. We are not yet gone to the cross product. We just identified the root map. What are the properties? Okay, important properties. The dot product of two vectors gives us a number. We know two vectors are orthogonal if their dot product is 0. It obeys the commutative law, right? This is the commutative law. And what it does, most important, is that the order of multiplication here doesn't matter. Remember, this is an important point, why I will tell you later. So what is the distributive property? Have you ever wondered? This is the distributive property. And remember here that this lambda part is a real number, right? Why I have mentioned it, do you wonder? The reason is that we can move out scalars in and out of each vectors. That is a remarkable part of the property of a dot product. So if you take a real number and we can move the scalars in and out, which helps us in a lot of calculations, which leads to this. It also follows scalar multiplication and all the bilinear properties. So these are the properties of dot product. So it will be just a quick recap. Few more are left. If we say AB equals to AC, then in general we cancel out A and with B equals to C. This is not the case. Cancellation is not allowed in case of dot product. This is the rule, and we can write this equals to 0. And it also follows it is not associative. That means if we follow the rule, then A dot B and vector C is not defined. Mathematically, we call it as ill-defined, right? So this is something which is not defined. So it does not follow the associative property, cancellation not allowed, and various other things. You might be wondering why I'm going deep into these properties instead of saying that what is the difference. You will soon understand. Just hold on for a few minutes more. Okay. So now we come to the importance of dot product. This is very, very important. What are the important properties that we learned of the dot product? Okay. So we learned that dot products obviously gives a scalar quantity. It measures how similar two vectors are, and that is why we measure the projection. That means how one vector moves along with that. Remember the simple example of you or your friend or your mate going out on a tour. If the vectors are perpendicular, obviously the dot product will be 0. It can be extended to n dimension. It obeys the commutative law, and we cannot calculate the area of a parallelogram using the dot product. Here lies the motivation intuition behind creating what is called a cross product. Okay, remember that the self dot product, so a dot a equals to a square, which gives root over a dot a within the radical. That means it gives a Euclidean length. It gives a line element, gives a Euclidean length, and obviously it is not associated. Now these are some of the important properties. Don't go by mistake that these are all the properties. However, I just thought that before we start and giving an idea about the difference, this is important. Okay, so now we come to the cross product, and before I go, I just wanted to tell you few of the fundamentals of cross product. The basic reason of that, you have done a lot of mathematics in cross product, but have you wondered that why do we need a dot product? Now, see, the thing is that we have a product that measures how similar vectors are, right? Which is the dot product, obviously. Now, the question is that can we construct a product that measures how different things are, how different things should be? Now, here is a parallelogram. Now, my question too is that can we construct an area product? We cannot, using dot product, obviously. So can we say that we can multiply A and B and gives the area that spans across the parallelogram? Can we define a useful product that returns a vector, obviously? This is the motivation behind doing the cross product, that we are trying to find out the area of a parallelogram, for example, and this is not possible with the dot product. Let us see how it is possible with the cross product. Okay. So first, the definition of cross product is it is a binary operation on two vectors in a three-dimensional Euclidean vector space. Remember, it is on three-dimensional Euclidean vector space. That means the question is that what will happen if we extend to three dimension to n dimension? Can we use cross product? Yes, on a specific manner. I am going to explain you that. And it is denoted by this sign, which is called A cross B. And if I go with the mathematical definition, it is something very cumbersome. I understand it looks like this. But don't worry. I'm going to give you a very simple formula through which you can remember which is crossed with this. Now, what we do is that this is the one which we are trying to find. Now, this is difficult. I understand. Now, so what we will do is that first we will recall from our linear algebra and vector analysis that the standard vectors in three dimension ijk are this, right? So to calculate the cross product of A and B, we can make a 3 by 3 matrix with ijk across the top row. Let us see, and the components of A across the middle row and the components of B across the bottom row. So you say this, here are the ijk, this is at the middle row and this lies at the bottom row. The next thing that we are going to do is that we are going to take a determinant, and I have shown that. I've already taken a determinant of this matrix, and finally it comes to this, right? It comes to this. So we have finally got the same result which we are started. So there are numerous ways in which cross products formulas can be remembered, but this is one of the ways. I'm not saying that you need to do that, but this is one of them, right? Okay. So what we do is that we quickly look into the algebraic properties of cross product. So the first algebraic property is that the self cross product yields to 0. It is anti-commutative. Remember, it does matter, right? Earlier we have seen that the dot product, it follows the commutative law. Here it is not, and we will also see intuitively in figure why it is anti-commutative. And distribution over addition. Okay, so we can move scalars in and out just like the dot product. So we get lambda and we can move out the scalars, which gives easy for us to do the calculations. It is not associative in nature, and just like the dot product, it also doesn't allow cancellation. That means we cannot say if A into a cross B equals to B, A cross C, then with A equals to not equals to C, it does not imply that B will be equals to C. Okay. So now we see that what is the geometric meaning of cross product, because this is important to visualize. Okay. So so we get the dot product as A dot B, which measures how similar these are, and this is exactly the different. It measures how different the vectors are. So the cross product provides a way to measure orthogonality, and this is how we measure the dot product. This is how we measure the dot cross product, and this n actually is the unit vector perpendicular. In certain cases, you might see some of the authors in books of mathematics and physics have ignored n, but I just thought to give you the answer. Now comes this one. So try to understand that this is by convention, right? The right hand rule. So the direction of the vector n is given by the right hand rule, but the only one simply implies that the forefinger of the right hand side is in the direction of A, the middle finger is in the direction of B, and then the vector n is coming out of the thumb, right? As you can see, it's coming out of the thumb. Now, if I use the same and I reverse it, that means I rotate this one. You see this one, it implies that the cross product is anti-commutative. So you see A cross B equals to minus A cross B. It should be A cross B. I've written B cross C. Anyway, by pointing the forefinger towards B first, if he points the forefinger towards B first, as I have pointed out here in the left hand side of the screen, the thumb is automatically forced downwards, and it is reversing the side of the dot product. So this is why it is called anti-commutative. I told you that we are going to see in visual what does it mean by anti-commutative. So this is what is meant by anti-commutative. Okay. So this is an important property. Cross product achieves its largest magnitude when A and B are orthogonal. Okay. Now there are two figures, right? Here there are two figures. And this one and this one, you can see that one is a little bit tilted and one is absolutely perpendicular. So obviously the perpendicular one gives more area because it is more orthogonal, and this one gives less area because it is less orthogonal. And what it defines from here is that now we have designed a formula that we can calculate the area of parallelogram just by multiplying A with B. Right? So now you remember that when we started the video, I told you that dot product, can we find out a vector so that we can find out the area of a parallelogram? It was not possible, right? Now it is possible. Why? Because the more orthogonal means more area, and just by multiplying A with B, we get the area of a parallelogram, and this is how we calculate it, which is right at the bottom of the screen. So the intuitive approach of geometric meaning gives us the area of the parallelogram, which is actually the vector and which we are aiming towards. Okay. So A cross B is a vector that is more orthogonal to A and B. We understand that. The problem is that given two vectors A and B, there are two possible directions which emerges that cross product would go. The purpose of this section of the video is that can we find out which direction it would go. So if this is the vector A and B, then this is the orthogonal part. Then either A cross B can be in this direction or A cross B in this direction, right? So we have a normal that strikes out either above or below. So which one it will emerge? Is it A cross B in this direction or A cross B in that direction? So remember that changing the order multiplication gives us the opposite direction. That means the right hand rule which we just saw, this one, if it is applied, then it will come to this, right? But whereas the finger is a little bit tilted around this area, I'm so sorry, then it will lead to anti-commutative law, right? So the changing of the order of multiplication gives a vector in the opposite direction. This means that the picture which I have just shown, one of the vectors will be into A and cross B, while the other will be B cross A. Which one is which? Now here is the right hand rule which I have shown. In calculating A cross B, we take our hand curl fingers starting at a point, and then the direction is this, and this leads to this conclusion, A cross B. Right, now the direction of that thumb is now pointing towards A cross B. Now let us take B cross A, right? And we take our hand and curl our fingers from B to A, the red zone. And you see this is coming, which is anti-commutative. B cross A equals to minus A cross B. That means ultimately A cross B is orthogonal to both A and B, and its direction is determined by the right hand rule. So this is quite clear, right? So from the right hand rule, we find the commutative law, whereas when we are reversing the direction of B along with A, the finger is pointing downwards and it is showing that it is not orthogonal, or it gives a direction which is just on the opposite direction. So this is again an intuitive approach which will actually give the direction which is being reversed, and you can understand from this figure. Okay, now we come to few of the important cross product properties. What are the important properties? Cross product of two vectors. Yes, it is a vector quantity. That is our aim. Cross product measures how different vectors are. Remember, now you're moving with your friend or your family or your mate, where everything is different, right? You are saying this, he is saying that. You want pizza, he wants steak. You want the color of the hat to be red, she wants the color of the hat to be blue. So we are measuring how different two vectors are. Cross product of two vectors are perpendicular to the plane, and we can now generalize the cross product. It is not quite clear. It is called 7-dimensional cross product. I'm not very sure. You can look into the Wikipedia. It doesn't obey the commutative, and it is called anti-commutative. We can calculate the area of the parallelogram, which is the basic idea behind this, because we really want to see that how we can calculate, because it gives a vector. The self product is A multiplied across A is 0, and it is not associated. Okay, these are the formula, and now we come to the real life applications of first the dot product and then the cross product. Okay, this is quite common. I think you all know this is a solar panel and this is the sun shining, and we draw a normal unit vector R which is straight coming out of the panel, and we draw another S which is pointing towards the sun. Right now, what the basic aim of the solar panel is to get maximum amount of energy. Now suppose with the passing of the day, and this is a theta angle, the sun moves to here, the black one, just beside this. Then we again have to change the angle of the solar panel which is pointing towards the sun, which ultimately gives you the idea that more the solar panels are pointing towards sun, the energy is more. That means the dot product will determine how much solar energy is absorbed. In this case, I have shown the simple formula. So this is application number 1, that as the sun moves, the alignment of the vector along with the solar panel gives the maximum amount of energy that the solar panel will get. This is a pretty straightforward application of dot product. As we move and things moves along, the angle of theta measures the displacement. So it lowers and lowers and lowers, and here it comes. And what happens in here is that the closer the force vector is to the direction of the motion, the larger is the kinetic energy. The more and more is the kinetic energy, right? So we use this formula, W equals to F dot D, and it actually shows the change in kinetic energy. This is the easiest, simplest, and the most common example of how work done is measured by dot product. Okay, in computer games also we use dot products. I just wanted to show you these 3 examples. Somebody is fighting. This is the Doom which is being fought between the demons and you. So the basic objective of all these examples is that it determines whether one character is within the field or in the vicinity of another, whether you get caught or fired, or what is the next course of action in the game would be. Now, how can dot product helps us to understand that whether the enemy is near or far, or you get caught up or something like that? I'll just quickly use a simple analogy. This is a game where this gun is pointing towards this monster, and you want to measure the direction, whether this monster is this far, it is hiding behind this pillar, or the wall is so far behind. So how can we measure? We do a vector analysis, and by measuring these directions, the game planner or the gamer actually makes the decision whether there will be a fire, you will get caught up, or whatever the action. So let us take this kind of a field, and here I am, a clown, and this is the monster, and I straight away draw a line which is the way I am facing. So the first unit vector which comes out of this is that where I am facing. So unit normal vector, where I am facing. Now I draw another vector which points towards this demon, and this is what the point is pointing towards the monster, and we get a theta angle. So what happens is that the sign of the dot product determines whether the player is in front or at the corner or hiding behind something, what is there and what is happening, right? So this is again an example. And how do we do that? We do that using the dot product and what is called vector analysis. So by using vector analysis, we find out that what actually would be the course of action for the gamer, what would be happening just by finding which way the angle of the vector is pointing, and that is done by dot product. Okay, some of the applications of cross product can we see? Yes, we know what is a torque, right? It is called a moment of force, the tendency of a force to rotate the body of which it is applied. We have all learned in classical mechanics. So the torque specified with regards to the axis rotation is equal to the magnitude of the component of force vector lying in the perpendicular direction. Another important thing, curl of a vector, which is also used by a dot cross product, right? Now you see here again we are using the right hand rule, and I have just mentioned how right hand rule implies cross product. So the thumbs point in the direction of n and the fingers curls along the orientation. So curl and torque are some of the two great examples. Now we come to the difference between cross and dot product. First of all, it gives a scalar quantity, cross gives a vector quantity. This measures how similar vectors are, this measures how different vectors are. Vectors are perpendicular if dot product is 0. Here cross product of two parallel vectors are 0, right? This obeys the commutative law. This doesn't obey the commutative law. This cannot calculate the area of a parallelogram. This calculates, and we have seen how vectors yields to the calculation of the parallelogram. This is a self dot product gives the Euclidean length. However, this doesn't give, it gives 0. It is associative, it is non-associative, and it is used for solar panels, computer games, energy momentum, plagiarism. If you really want, you can see into the other video of cross and dot product, but just I have explained in details the concepts. It is there in the I button. You can just click on watch it. It is used for calculating torque as it is a vector quantity. Remember, it is also used to calculate the divergence of a dot product. Cross product is used to calculate the curl. And in metrictensor, it is used in general theory of relativity because it measures how one vector is a friend of other that is going along with that. And here it is nothing like that. These are the major differences. However, there might be other differences. You can put it in the comment box between the dot product and cross product. Finally, we come to the last part of the video where we will just quickly see that how dot product is used in general relativity dealing with metric tensor. Okay, so first of all, the metric tensor is used to define lengths of geometric properties. Again, you see the metric generalizes these properties. Remember, what does dot product do? It measures how one vectors move alongside with another vector. That means how similar things are generalizing in other way, right? And it calculates the line element of the matrix. So if you get a kind of a curved space like this, I'm just taking 2 dimension. You can imagine to be 4 dimension. X being x1, x2, x3, and time being the t direction. And we get these 2 vectors, right? So I will just put up the earlier one, u dot v. This is the basis of the vectors. It is showing in the x direction, the blue one, and the black one is showing in the t direction. So what it measures is that this one basis vectors measure time in the t direction, and this measures basis vector x in the x direction. And remember that because we are dealing with curved space time, we cannot say this one equals to this. Because we are dealing with curved space time, we need to introduce another method, another property, which is called the metric tensor. So here you can see that how dot product actually measures the movement of the vector along the curved space time. We follow the same kind of a illustration. We use metric tensor now, which is the G1, which is a correction factor to each term in the dot product. That means basis vectors may be different from place to place, and because basis vectors are not constant, because we are not dealing with orthogonal perpendicular planes, we are dealing with curved space-time. This is the one which gives us the answer, and G is the metric tensor, which actually shows that the components of 2 index tensor rather than vector components. So this is a very nice, you can look into my video, I think it is called Richie tensor video, where I have explained this dot product in details. So you can see that how the basis of the vector is changing, and in order to do a correction, we introduce the metric tensor, and in order to do that, we are using dot product, because we are measuring the movement of the vectors along with this. So finally we come to this part, and here you see the basis vector in the time direction t and basis vector in the x direction. So gxt equals to g sub x dotted with g sub t. That means that in some notation you will see g mu nu equals to e mu dotted with e nu. It actually gives that the metric tensor is defined as the dot product between basis vectors. Now I hope you can understand well why it is a dot product between two basis vectors, because in general theory of relativity, the entire central idea is to get a similarity between vectors. So if I can see that Ex is moving in this direction and Et is moving in the t direction, then what would be the movement of the next vector? So that we can understand what the next vector would be moving, what would be the curvature, blah, 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 all those details. This gives you an idea of using dot product in metric tensor and why we use dot product, right? So strictly speaking, the metric is the dot product between two basis vectors. This is what it does. So generally we think basis vectors are orthogonal, but in non-Euclidean space it is not orthogonal. So it essentially tells how much two vectors are aligned with each other. Remember, in the starting of the video, I told you that we are using this as an intuitive approach, that how much one vector is similar to each other, and it essentially is now boiling to the same point that in curved spacetime using metric tensor, this is how the vectors align. One important thing is that we use divergence. In divergence, we use a dot product, right? This is the dot product. Whereas while mentioning curl, we mention cross product. The quiz that is coming up, or you might answer it's up to you, is that why in divergence we use a dot product and why in curl we use a cross product. All right. This would be, I would try to answer it in my next video. I'm not very sure. I need to do a little bit of research. If you have the answer, please do comment. So this is the difference, the understanding, the intuition, and as I promised you, at the end of the video, you're going to get a complete deep understanding along with the practical applications and difference. I hope you like this video. Do please put up your comment, like, and your click on the bell icon to get all the notification for Physics for Students. I hope you enjoyed this video. I'm signing off as of now, promising to come back with another interesting video. Till then, have a nice week and have a nice weekend ahead, and I will be back with another video. Till that time, goodbye and have a nice time. Bye.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.